Hi there! I have here on my breadboard three DS18B20 one-wire temperature sensors controlled by an Arduino, and as you can see, I'm plotting the temperatures they're reading. If you want to know how such a setup works in software and the wiring, the hardware, the schematics, I made a video about that. Card link. Anyway, I want two of these sensors to be galvanically isolated from my Arduino. That is, I need to galvanically isolate one-wire buses. And that's exactly what we will do in this video. You might ask yourself, why would I want to galvanically isolate a one-wire bus? I already did a video about galvanic isolation of an SPI bus, card link, and there are good reasons for that, at least when you are measuring temperatures with thermocouples and max 6675 chips. The reason being all these thermocouples are electrically connected, and you can use two of those to short out things. So galvanic isolation there between your different thermocouples is a really good thing. But why for the one-wire bus? Example number one. Your one-wire bus runs in the same cable as mains AC, and you are somehow paranoid about sharp conductive elements cutting into the cable and shorting out the live wire of mains to your one-wire bus. Example number two, your one-wire sensors, in my case DS18B20s, are in the same case with some mains AC, and the case is in kind of a danger being flooded with a conductive liquid like a base or acid or simply water. Third and last example. Some people use the one-wire network to measure the temperature in their garden or in their glass houses. So the wires run outside. So what do you suppose happens when lightning strikes? I mean, hopefully you have here somewhere a box with overvoltage protection that is grounded. But some galvanic isolation here really helps your electronic equipment, whatever reads the one-wire bus, to survive. The first obstacle we have to overcome in our quest of isolating a one-wire bus is to find a suitable chip that does that. And for SPI, that wasn't a problem. I'm here at the DigiKey digital isolator section, and you see for SPI there are 66 chips in stock that just do that. However, if we look here in the type filter, we cannot find one wire. There are no chips especially designed to galvanically isolate one wire, but we find I2C. And these chips should do the job, and there are lots of them, 94, and I said I need two channels, and I need them, of course, bidirectional, that is two inputs on both sides, or we could easier say bidirectional, should be the same. Still 32, and if we apply the filter, and I already said in stock and few prices at 1, the cheapest one we find is the Silicon Labs SL8600. And, well, guess what? Reaching here for one. I have one here. The bidirectional I2C SDA serial data line works as follows. It's normally high, pulled up by a resistor to VCC, typical value 4.7K. And the I2C devices, when they want to signal something on the bus, they pull it down via, if it's a CMOS, open drain, or bipolar open collector output here. And if they're just reading that, what's going on the line, there's an input buffer, and that buggers off here somewhere to the internal logic of the I2C devices. However, this looks exactly like a bidirectional one-wire line with direct power. So, sorry, no parasitic power in this video. Maybe another time, but it's exactly the same, down to the typical value of that pull-up resistor, 4.7K. And, well, to be obvious, sorry, that's the reason why a digital isolator for I2C should also work for one wire. Well, we'll see. If we look into the datasheet of the SI8600, sorry, not SL, SI8600, we see here an I2C device, like I've just drawn one, and the other I2C device and the pull-up resistors, and that chip that does the digital or galvanic isolation between the two buses between it. And you see it has some bidirectional stuff also going on, working in one direction and in the other. And a few pages further in, we find that typical SI8600 application diagram. You have one side here, with a VDD or VCC and a ground, and you have here isolated from that the other side with B VDD and B ground. It's completely symmetrical. You have two bidirectional data lines, okay, and they are both pulled up on both sides by pull-up resistors. Okay, here they're using 3Ks, but in Arduino world for I2C you usually use 4.7K, and that's completely within what that chip can do. And your two decoupling capacitors. I think it's time now to put one of mine on the breadboard and just try that. One last look at the status quo of my breadboard before I add my SI8600 to it. My three DS18B20 temperature sensors, my three one-wire buses, each with a pull-up sensor to the 5-volt rail, and direct ground and direct power connection. So my unisolated Arduino power rail is up here. And I will show you a schematic of the completed circuit, if it's working. Now I've added the SI8600 to the equation, and it's just like in the datasheet, okay? My two data lines from the Arduino go into the two inputs of one side of the chip, and I still have my pull-up resistors here for the data lines, and the chip gets, its power supply from the, let's call it, unisolated power rail from the Arduino. And from the output, not really output, it's bidirectional, but on the other side of the chip I have my two data lines going to my temperature sensors, which still have power supply, but now from another rail, and I have pull-up resistors here too on both one-wire buses. And of course on that side I need another power supply. Now the only thing missing here, or basically it's cheating, I bridged both power buses. Okay, we will alleviate that in the next step, but let's first see if that thing really works as I promised. And indeed it does. My temperatures are still happily plotting away. The difference between my non-isolated, they are not really isolated yet, temperature sensor here and the others, I can raise it too, is basically I handled them. So they are a wee bit warmer, but they are working. And I can make a 3-phase AC here just by touching them. Isn't that cool? Okay, maybe not quite, but you get the idea. Looks good. Okay, next step is we have to introduce an isolated power supply for the B side or second side of our digital isolator. Let's do that. I've added the last variable to the equation, and that is an isolated, unregulated DC to DC converter. 5 volts in from the Arduino and 5 volts out, isolated to my isolated power rail here. So I don't expect any problems, but let's check if that is working. And it's working. 2 completely isolated one-wire buses. Great. By the way, I'm measuring here my isolated power rail. Just a precaution, because obviously I felt lucky and put in that DC to DC converter without doing any measurements or calculations if that thing has enough load. That is at least 10%, because its operating range is only between 10 and 100% load. I made a video about these thingies too, card link, and maybe as a bonus later on we will put the oscilloscope on here, because you see I have some filtering around that DC-DC converter, and see how that works out. But anyway, now let's have a look at the circuit diagram for the whole thing. As promised, here the complete circuit diagram of what was on the breadboard. So I have my Arduino Nano Avery, a card link, and this gets power via USB and provides 5 volt to everything that's left of the red line. We have our single non-isolated DS18B20 slaving away on a one-wire line here connected to D2 with a pull-up resistor, as it's custom for one-wire buses. And I have 2 more one-wire buses here from D3, D4, each with a pull-up resistor going into the A side of my SE8600. And I forgot to draw in the decoupling capacitors here for the A and B side. We also have this unregulated, isolated DC to DC converter, 5 volt to 5 volt, gets its power from the Arduino and provides isolated 5 volt power to everything that's right off the left red line, including the B side of our SE8600. And there on the B side, our one-wire buses emerge again. Each got a pull-up resistor and each is connected to one of the isolated DS18B20s. That's it. And just to be complete, a quick look at the Arduino code. So I'm using the DS18B20RT library by Rob Tillett. Yeah, a card link to drive my DS18B20 sensors. And I have, defined here my 3 pins of the Arduino where the sensors are connected. I'm initializing 3 one-wire buses, one for each of the pins, and I'm initializing 3 of the DS18B20 objects, one on each one-wire bus. Setup is quite simple. Serial begin. I need that to get anything to the serial plotter. And I do an sensor begin, 3 times and check if, a sensor is actually connected. And then I set the resolutions of all 3 sensors to 11 bits. The loop itself is most primitive. I request the temperatures for each sensor, then I wait 500 milliseconds, and then I print out the temperatures. That's it. If you want to know details how that DS18B20RT library works, have a look at the video I put a card and a link to. Let's move on to the bonus features. Let's first talk about why these bidirectional digital isolators work at all. Because if you start to think about it, it's absolutely not trivial. And as a side note, the picture given here in the datasheet is not complete. I will try to draw a more complete picture later. Let's assume for the moment that absolutely nothing is happening on the bus. So both devices here are high impedance on their input, just reading what's going on, and the bus on both sides is naturally pulled high by the pull-up resistors. Now that device wants to signal something and pulls the bus low. It has the same inputs like that, so there's a little training here which can be used to pull the bus low. So our digital isolator reads that the bus is low and in turn pulls the bus on the other side low. And the low signal arrives here at our other device and is read. However, now the bus is low, our digital isolator reads that side of the bus low and in itself is pulling this side of the bus low, which in turn, it reads it's low and pulling here low. You see the problem. That is called a latch or a latch up. So once you pull the bus low on one side, the digital isolator will make sure it's pulled down on both sides low for all eternity without any additional measurements. And here comes some information from the datasheet where it says output low VOL and input low VIL, blah blah blah. VOL is greater, so output low is greater than the input low to prevent the latch condition. So I will try to make a better graphic. Here it is, but before we delve into the hardware details here, let me explain one thing. A digital isolator treats the data line not as a two-state line, high and low, but as a three-state line. Of course, there's high, 0 volt is down here, our high is somewhere up there, pull-up resistor to 5 volts, but it knows 2 different distinct low states that have an invalid voltage band between them. And they are called input low, which is the lower one of the two, and output low. Okay, now let's go to the graphic. In the datasheet there were these voltage sources inside the circuit, I'm using here 3 different voltage rails. Yeah, we have our ground rail, we have our input low voltage rail, and our output low voltage rail. Yeah, the same on the other side of the isolator. So basically, if I get a signal in here, yeah, to pull the bus low, my MOSFET pulls the bus low, but only to that rail here, to the output low rail, which is voltage-wise above the input low rail. That means if I'm pulling the bus low here only to VOL, yeah, on this side, the input stage, which is a comparator, compares my bus voltage to the input low, which is lower, and therefore doesn't pull down by itself the other side of the bus. Now, that has certain implications for the compatibility of our bus devices, okay? So our bus devices, yeah, if we say, okay, they also have an input low and an output low, but, usually these are overlapping devices. Doesn't matter if it's I2C or one-wire devices, yeah. They can pull the bus low into a certain band and they will recognize the bus is low in a certain band, which is usually bigger. But in our case, our bus devices must be able to pull down the bus below the input low of our digital isolator. And they must be able to recognize that the bus is low up to a voltage level that is at or above the maximum output low of our digital isolator. So that in our example, we took an I2C digital isolator and it worked with our one-wire devices, which are probably slightly differently spec'd in that regard. Was kind of luck. Okay, next, get out the oscilloscope and look at the filtering of the DC-DC converter. I'm measuring here the noise of the Arduino 5-volt rail, and it's about 200 millivolts, and that's all noise from the USB power supply from my notebook, because, yeah, I haven't even connected the DC-DC converter. So let's do that next. Well, with the DC-DC converter connected, it's about maybe 210 millivolts, so yeah. Now that's my isolated power rail, and yeah, naturally I cannot measure both at the same time because, through the oscilloscope I would short out both grounds and that might, influence the measurement. So let's not do that. Much more interesting. I'm at a time scale of 100 milliseconds, and you remember I tell those thingies here to make a temperature conversion every 500 milliseconds. So this is really the instability of the unregulated DC-DC converter when these thingies here try to draw some current when they do their conversion. And yeah, but it's also 200 millivolts. So let's talk about how I derived at these values for the input and the output filter. These are the informations from the data sheet of my 100 milliwatt DC to DC converter in regards to, typical application circuit with filtering and EMC compliant class B filtering. And that's really the data sheet. However, they have some recommendations for their 250 milliwatt model. That's the recommended circuit for their 250 milliwatt model. And the astute amongst you noticed that my circuit has nothing to do with that at all. We will correct that in a second. Anyway, for the 100 microwatt model, I decided, to divide all the values by the factor of 2.5 because, 250 divided by 2.5 is my 100 milliwatts. And so with some rounding errors, I get, for the inductivity, 2.2 microhenry instead of 6.8, 2.2 microfarads for the input capacitor instead of 4.7, and 4.7 microfarad for the output capacitor instead of the 10 microfarad. But let me correct the circuit, build it properly, and So the size of the input and output capacitor was okay on the breadboard. I just put the wrong values here in the circuit diagram. However, on the breadboard at the wrong position and also on the wrong position here in the schematic is a 2.2 microhenry inductivity. This inductivity, this RC element here, is not for filtering the input voltage, but it's to prevent any ripple currents that are created here by the switch mode stuff to leak out into the 5-volt rail. So that's the wrong way around. I mean, it's an RC low-pass filter, okay, and it works that way around. Okay, that little change in the filter obviously didn't change anything for the output side, but let's look again at the Arduino 5-volt rail. Nothing changed here either, so that makes you wonder, of course, do we need that filtering at all? So I removed the input filtering on completely, and no change, 210 millivolts peak to peak on the 5-volt Arduino power rail. Maybe it's the same for the output filtering? Let's see. If anything, the noise on my isolated 5-volt rail, just with the input filtering removed, it went down to about 175 millivolts. And we can now live pull the filter capacitor at the output, and absolutely nothing happens. Not that I like that, what I'm seeing here, but it shows you there was a reason the datasheet had an empty page on filtering. But anyway, maybe we can do a little bit better than that stuff. Anyway, that's my output rail, with two 470 ceramic capacitors in parallel, the little blue blobs here, and it does really not much till nothing. So this was really low impedance ceramics. The only thing I can test now is, adding one of those to the input. And for the output side, that 407 nanoceramic does, as expected, nothing. But let's have a look at the input side. Maybe something changed there. Nah, doesn't do anything either. We are still here about at 210 millivolts. And if I pull that capacitor here again, you see maybe some spikes, but just to give you an idea in which regions we are measuring here, I can pull the plug of the power supply, and that's the bass noise. Okay, we're getting here with our measurement setup. So yeah, we are more than fine without any filtering for that DC-DC converter, and now we know why the sheet was empty. Yeah. Anyway, better safe than sorry, and see you next time. Bye.